Okay, we're going to look at how we can figure out the shapes of molecules, aka the molecular shape or molecular geometry, as well as the kind of full picture of a molecule we call the electron geometry, based on the electron domains of bonded atoms and lone pairs of electrons, using valence shell electron pair repulsion theory, a lot of times shortened to VSEPR theory. And sometimes we just shorten even more and say Vesper or something like that. So Vesper theory or VSEPR theory is basically just a way of saying when we have things with electrons near each other, they're going to repel each other. So in order to make a stable molecule, we're going to try and put those groups of electrons as far away as we can. Those groups of electrons can come in terms of bonded atoms, which I'm going to show as an X. Okay, to some central atom, I'm going to use A to show that. Okay, and again, we try and put them as far apart from each other as we can. Go. Or it could be a lone pair of electrons. So here's a bonded atom, and then I've got a lone pair of electrons here, which I'm going to do one of these. Okay, so in either case, these need to have their room. They're going to repel each other. So we're going to put them as far apart from each other as possible. This gives us certain three-dimensional shapes. Now, if you are not super great at visualizing things in your head and seeing how things will move around and kind of spinning a 3D shape in your brain, that's okay, because we have a method that helps us figure out what a molecular shape or what an electron geometry is going to be, just based on what's bonded to the central atom and how many lone pairs the central atom may have. Okay, we call this the AXE method, or the AXE method, where the A stands for the central atom. Central atom. The X stands for bonded atoms to the center. We don't count the center in bonded atoms. Bonded atoms. Okay, and E, which is lone pairs of electrons. Lone pairs. And do be aware we are counting pairs of electrons, not just single lone electrons. Lone pairs of electrons. Ooh, that was a really bad E. Let's try that one again. That's a little better. There we go. So if I wanted to figure out the shape of this guy down here, I could make an AX code for it and look it up on a thing called a VSEPR chart that would help me figure out the electron domain geometry and the molecular geometry or molecular shape for that molecule, for that chemical. So for this guy right here, I've got my central atom, and I'm always going to have a central atom that we're just going to call A. Okay, and then for the X and the E, we're going to have a number down here, kind of like when we write a chemical formula that tells us how many of those we have. Okay, so for instance, in this case, I have one of these X's. Okay, I have one bonded atom. So I would put a little 1 down here to signify, hey, I've got one bonded atom in this structure, in this chemical, in this compound molecule. Okay. Now I also have one lone pair of electrons. Okay, and I have, again, a pair. So for E, that counts as one pair of electrons. Okay, so there's my bonded atom. There's my lone pair of electrons. Okay, so the code for this would be AX1E1. You could shorten this and say, you don't really need to write the ones. It's implied that there's at least one if we write it. So kind of like a chemical formula, if you want, you can erase these ones. It would just be AXE as the code for this. But you can also leave them. There's nothing super wrong with that. On the assignment that we have, I like to include the numbers. So that way, things get checked better, and it makes more sense. You can, specifically say there's 1 or 0. Sometimes if you leave it blank, it's like unclear whether there's 1 or 0 there. So we're going to write the numbers in my case. But if you look this up on a chart, you might see these numbers kind of vanish. Okay. On a molecule like this over here, we still have a central A, and the A never changes. It's just going to be 1A. We have an X here and an X here, two bonded atoms. So I would write AX2. And in this case, I have no lone pairs of electrons. So I would write E0. That would be my AX code. Now, again, you might see it simplified and say, well, hey, if we don't have any lone electron pairs, why are we even writing the E? So you might see them get rid of that. And that's fine, too. You could also just call it AX2. But I like to write it out with the whole thing, just to be very clear, AX2E0. So what you can do with this is go look on a thing called a VSEPR chart, and I'll tell you what the molecular shape of this and the electron shape of this is. So if I go look up the code for AX2E0, that gives me an electron domain geometry shape of linear. And a molecular shape of linear, which means when I'm taking into account all my electrons, the shape of this thing and all the electrons in there is linear. And when I ignore the lone pairs of electrons, it's also still linear. Okay, so in this case, it doesn't really make a huge difference whether I'm talking about the electron geometry or the molecular shape because there are no lone pairs of electrons. Let's look at one example where the lone pairs of electrons do matter. Let's go to, we'll do this one, NF3. So let me draw out NF3. Nitrogen is my center atom here, and it starts with 5 valence electrons. So I'm going to do 1, 2, 3, 4, 5. I've got, well, let me do this. I've got 3 fluorines to bond it to, so bam, bam, bam. I'm going to put 3 fluorines there, and each has 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7 valence electrons. This is going to look a little sloppy. That's okay. I'm going to bond each one of these to each one of the fluorines. Okay, so if I were to spread these out evenly, your gut instinct might be to say that this is kind of like a triangle shape, what we would call trigonal planar. But let's figure out the AX code and see if it matches. Okay, so my central atom in this case, I'm going to use this blue, is A. I have my nitrogen is A. My X is my bonded atoms. I'm going to use red for these. So I've got 1, 2, 3 fluorine atoms bonded to this. So this would be AX3. Okay, and then for my lone pairs of electrons, I'm only counting what's on the center atom, and I have 1, 2 electrons. That's one lone pair. And on all the examples here, we're not going to have like an odd number of electrons, like 3 or 5. It's always going to be pairs. It's going to be 2 or 4 or 6 to make 1 pair or 2 pair or 3 pairs and things like that. So I have 1 pair of electrons here, and that's going to be my E. So this is going to be AX3E1. So this is my AX code, AX3E1. Okay. Now, the electron geometry for this, I can go look this up, has 4 electron domains. We would call that tetrahedral. Tetra meaning 4, and hedral meaning something about a shape. Don't know the exact definition, but something about a shape. Yeah, a shape with 4 points. Okay, for our 4 electron domains. Okay, but what we take into account for the molecular geometry or the molecular shape is only the bonded atoms. I kind of ignore this E1. Now, it still pushes things around, but I'm only looking at what the shape of the bonded atoms is once they're pushed by that lone electron pair. So if I go look at the AX3E1 code and I look at for the molecular shape or the molecular geometry, I'm going to put shape here because they were going to mean the same thing. Molecular shape, AX3E1 has a molecular shape of trigonal, as in 3, like a triangle, trigonal pyramid. Okay, where these fluorines kind of make a triangle pyramid going up to the nitrogen atom, and we kind of leave out where the lone pair of electrons would be. So they're still pushed out of the way, and we end up with a shape that's kind of like this. If you can see my 3D shape there, it would have something kind of in the back. Okay, something like that, where my N is here, and I've got my fluorine, my fluorine, my fluorine there. Okay, so this just goes to show that if you have a hard time visualizing things like this in your head, the AX code is perfect for figuring out the electron shape, the electron geometry, okay, where we have the full picture of where all our groups of electrons are, bonded atoms or non-bonded electron pairs. Okay? And also help us figure out the molecular geometry or the molecular shape, where we kind of ignore the electron groups that are lone pairs of electrons and only look at where those bonded atoms end up. Okay, which is still affected by the lone pairs, but we only look at those for the actual molecule shape. So we kind of cut away from the electron geometry to figure out the molecular geometry. Okay, so for all these examples, try and draw out the molecule, figure out the AX code, and that should help you figure out either the electron geometry or the molecular geometry. Okay, and in each case, I think these are all molecular geometry. The electron geometry is going to be kind of, again, the full picture. The molecular geometry will be kind of the cutaway part where we can kind of ignore the lone pairs of electrons and look at where those bonded atoms end up.